So our next speaker is Alex Robinson from the University of Liverpool, and he will talk about in silico pictography of lithium battery cathode material from subsamples for this STEAM data. So yeah, the floor is yours.
Thank you very much, and thank you to the organisers for having me here. As has already been discussed, we've had a lot on electron microscopy, specifically STEM, and today I'm going to be talking about how we can take advantage of subsampling for multidimensional electron microscopy, in this case, 4-dimensional STEM. I'm going to be applying this to a very hot topic at the moment in materials science, which is lithium-ion cathode materials. So firstly, Nigel has already spoken about this a lot, and so has Daniel, but the fundamental to all of this is electrons. So the beauty of electrons and quantum mechanics for that vein is that they, under certain conditions, can have wave-like behavior. And Louis de Broglie, I probably just butchered his name, so sorry for French-speaking people here, in his PhD thesis postulated that with a certain momentum, an electron, or any matter particle for that matter, can behave like a wave. And because of this, we can use electrons to probe very, very small distances, in our case, on the atomic scale. But it's all great, this theory. How do we then implement it? So it was actually chap Baron Manfred van Arden who built the first STEM in 1938, but it was destroyed during World War II in an air raid. And it wasn't until the 70s when Albert Crew then began developing STEM again. And essentially we've got our probe forming system. We form a condensed probe onto our sample, and then we're going to collect signals as they transmit through the sample. Now, this is all great. And then when Krivenik began developing aberration correctors in the 2000s, at the turn of the millennium, we now have probes which are brighter, smaller, and more coherent than ever before. And this is fantastic if you want high resolution, but there's a huge amount of samples out there which simply don't like electrons. They don't respond well to these electron sample interactions. Now, we call this beam damage, and we've alluded to this earlier, but there's two main types of beam damage that we talk about. So we've got this knock-on damage, which you can think of as being like in pool. If anyone plays snooker or pool, we fire our electron at an atom, it's then going to displace that atom from its equilibrium position. And then we can end up with cascading effects and the formation of deformations, defects, that sort of thing. And then we also have this radiolysis, which is essentially ionization of our sample and cleavage of chemical bonds. So all of this basically means that our sample, which we wanted to investigate, is no longer in the same state that we intended. And then this can lead to poor analysis of your samples, and you can't quantify really what it is you were looking for. So to mitigate this, there has been several attempts to try and mitigate this using standard approaches to electron microscopy. So that's low dose methods. So here we have an example of low dose, where essentially we're down to a handful of electrons, and this is a typical unit to measure the dose rate of our electrons. Is essentially how many do we have inside an angstrom squared. Now you notice this is the large field of view. So in this case, we can do that. But as we start going down to the atomic scale, then our number of electrons per angstrom squared there, we need more. If we were to go to these sorts of doses, we end up with just too much noise in our images. Another way to mitigate that is through cryo-EM, where we, as we said earlier, we freeze it in ice, and then we can hopefully slow down that radiolysis process as well. But all of this takes a long time to acquire and can come at a cost. So to update an existing microscope with a cryo system is very expensive, and you also need certain expertise to be able to manage this. So we're now looking into this idea of probe subsampling, and there's been plenty of papers out there so far where we're looking at how can we overcome this issue of beam damage, acquisition time, and signal to noise through essentially subsampling our data sets, subsampling the locations where we send our probe to. Now, this is this is actually pretty tricky to do in practice. So to do that, we need essentially, we've got this 3-step process where we start with a way of controlling where our probe is. To call this a scan controller. Then that's going to feed information to our scan coils. And then that's going to then tell our probe where it has to go. And then we're going to record whatever signal we're interested in at that probe location. Now, as Daniel spoke about earlier, this itself is very difficult to be able to track where it has come from. But for the sake of this presentation, we're going to assume that all the probe locations that we've been to are the correct corresponding data. So after we've subsampled the data, we need to inpaint it. So for that, we use this BPFA algorithm, just a dictionary learning algorithm. There will be a demonstration tomorrow afternoon during the show and tell, tomorrow morning, sorry, where we'll show this in action. But essentially, we're trying to learn the dictionary which best represents our image. And then we can reconstruct from less than 5% of the total input data. In some cases, we can go even lower. Okay. So now that we have this idea of how we can reduce dose and keep our signal high, we're going to start thinking about what are the samples that we're really interested in. So at the moment, there's a big drive towards battery materials, because as we start using greener energy, we start having to store that greener energy because it's a direct current, so it's stored in batteries. So then we want to know, okay, what are the limitations with the current battery technology? So battery pretty much works like the figure on the left. There we go. So we have essentially our cathode material, which will contain lithium initially. Then what happens is we apply a potential across the anode, the cathode and the anode. Our electrons move through the circuit at the top, and our lithium diffuses through this interface and then sits. Usually it's something like graphene, where it'll just sit in between graphene layers in the anode. And then what will happen is when you discharge that battery, the lithium is going to migrate through again. But something very annoying happens for the lithium. So we start out with this nice layered structure, and the lithium will sit in these channels here in between. So we've got nickel here, and then we've got oxygen, and then we've got lithium, which will sit in this dark region here. We can't see it because lithium's very light. But then what will happen is you start to cycle this battery, the actual structure of the cathode begins to change. So initially the lithium was very happy moving in and out of these channels, but now it's being restricted by essentially what's happening. The nickel is taking the seats of where the lithium should go. So it's like if a few people left this room now and we took their seats away and they came back, they had nowhere to go. That's essentially what's happening. And that's why, one of the reasons why these cathode materials tend to degrade. So now we have a motivation as to why we want to look at these materials. But as I said, lithium is very hard to image and it's very light. It's got a weak scattering cross section. So you can see here in these figures, there are ways in STEM to get around that. So aberrations, as I spoke about earlier, we have these aberration correctors, but there's certain aberrations which we can't particularly correct for, or we have to try, and you have to be well trained to align the probe. And as we see, one of the best ways to try and view lithium is through this annular bright field imaging, but this is really sensitive to these residual aberrations. So you'll see aberration coefficients down at the bottom there. And if they're only slightly off the optimum condition, then it's going to disturb the entire image, and it's very difficult to actually see the lithium. And what you want to do is you want to be able to see how that lithium is migrating in and out of the cathode. Okay. So is there another method? So there's 4D STEM. So with 4D STEM, particularly for this talk, we're going to be talking about ptychography. Okay, so in 4D STEM, we essentially, at each of these grid locations in our raster scan, we're going to collect a convergent diffraction pattern, which is one of these guys here. So these are two-dimensional images themselves, which correspond to a pixel location in our 2D scanning grid. Now, using this information, we can perform various data analysis methods. So this can range from applying virtual detectors, So in the case of annular dark field imaging, we can apply a dark field detector, a virtual one to that. We can also get out information about the charge distribution, the electric field of our sample by using differential phase contrast and center of mass. So we can understand how much the beam has been deflected by whatever it interacted with. And then the one which we're particularly interested in is ptychography. Okay, well, I mean, this has been shown to be one of the most robust methods for actually imaging and understanding what's happening within your sample due to the interactions with the beam. Now, 4D STEM, this all sounds great, but it takes a very long time to acquire the data, which means that you are then limited by beam damage, again, cumulative dose, and then also potentially your stage actually drifting. So then you start misaligning between where the information came from and what we actually observed. So we want to try and think of a way that we can mitigate for this. And for that, we're going to consider subsampling. So as we see here, so we've got the same aberrations as before, but now instead we're using ptychography, particularly the Wigner distribution deconvolution algorithm. So here we can see that we can actually correct for those residual aberrations by having an estimate of our initial probe. And this is fantastic. It means we don't have to worry about these aberrations, which we couldn't correct for during alignment and during imaging. As long as we can estimate those actual aberrations, we can then correct for them in post-processing. Now this looks like magic, but how does it actually work? So what we're going to do is, this is our object. This is the thing that we're actually we're interested in, our sample. We have our probe, which is this guy over here, this guy over here, okay? And then we have our seabeds over here, okay? And what we want to do is, as you can see from this equation here, our seabeds are a convolution between our initial probe and then the object that we're actually trying to look at. So we want to try and separate the two out. Okay, to do that, we're going to use this algorithm. Now, there's a lot going on here, but the crux of the matter is we have our seabeds, okay, and we want to get to a point where we can estimate our actual object in real space, or the phase of our object. To do that, we're going to apply essentially a series of Fourier transforms and inverse Fourier transforms, and then also include a Wiener deconvolution in there as well. And then from that, we can extract this guy, the D matrix. Okay, that's what it's called, the D array. And then from there, we can apply one final inverse Fourier transform and extract the object, or the phase of our sample in real space. This is not the only method that can be used. There are this was one of the first developed by Bates and Rodenberg, sort of the turn from the 80s to the 90s. Nowadays, iterative ptychography algorithms are very popular and being used a lot within the field, especially for biological imaging, where we use what we call defocus probe ptychography. We try and illuminate a large area of the sample. This is just one of the ones which has been proven for focus probe ptychography conditions as a good way to estimate our object phase. Okay, so a quick checkpoint, because that was quite a lot. So our motivation to start with was to try and look at lithium-ion cathodes, but the issues we find are they're very hard to image using traditional STEM methods, and it takes a long time to acquire the data, which leads to damage. So we thought, okay, to actually image these samples, we'll use 4D STEM, and then to mitigate for the acquisition times and beam damage, we'll use subsampling. So then this leads us into subsampled 4D STEM. Okay, so how do we actually do that in practice? So what we're going to do, we're going to acquire just a subset of those probe locations. That's going to give us a subset of these diffraction patterns. Then we're going to sequentially fix our KD. So here we have our 4D STEM data. It's a function of the diffraction pattern locations and also the probe locations. And then we're going to fix KD and we'll form what we call a virtual image. That's essentially an image that corresponds to the same diffraction point for every one of the probe locations. Then we get a stack of these virtual images, which are going to inpaint sequentially using our inpainting algorithm. Okay. This solution essentially means that we can inpaint 4D STEM data. Now, it's not the only solution. One of the things postulate is that we can inpaint the entire 4D data set using a multidimensional dictionary learning algorithm. That's something that we have been implementing, Liverpool trying to implement, but this case is suitable. It's suitable in this case to do it this way. Now, when we apply the method, so our simulation setup, so we've essentially simulated some cathode materials using infinite dose. What this simulation is in practice, essentially going to form a probability distribution for each one of those probe locations of where the electron might go on the diffraction pattern. Then from that, we can then infer, we can apply different noise levels based on actual microscope conditions. So based on the probe current of our actual beam. And then from that, we can deduce the noise. And then we're going to then apply our probe subsampling and then pass it all through BPFA and see what we get. So here we have the references. We've got the reference phase and we've got our annular bright field image as well. So you can see here the lithium, because this is nicely aligned, it's simulated. You can see the lithium there, and in our phase images, you can see the lithium in those channels there. Okay, so first result where we have infinite dose, so we're not worried about noise. We can see that down to about 25%, we're getting reliable results. Then something strange starts to happen at 12.5%. We get the streaking. That's probably caused by the actual resolution of the image and then the inpainting algorithm itself. But down to these sorts of levels is pretty good. 25% is pretty standard. We want to go down even lower, so perhaps using a multidimensional algorithm could help with that. Then when we start to add more noise, so here we're simulating a 2 picoamp probe current, which is pretty low by standards in the field. Typically, most stems will operate about 12 picoamp. So here we're down to a sixth of that. At Liverpool, when we do low dose, we go even lower. So we go to half a picoamp in probe current. So that's about a 25th of what's typically used within the field. And again, we can see that we're getting reliable reconstructions even with the noise, which, given the fact that BPFA is designed with Gaussian noise in mind, here we've got Poisson noise. It's actually doing a pretty good job. Okay. Now for the phase images. So again, for infinite dose, we can see that the phase images are a lot more robust at the lower sampling rates than the annular bright field, which is great. That's what we were sort of hoping for. We hypothesized. So we can then now start adding noise again. So now we're starting to see the some artifacts caused by the addition of noise, especially down at the low sampling rates. And then we have something quite strange happening at this. And I left this in because this is something that I'd like to discuss with someone about, really, is why do we see that at these higher sampling rates, we get a drop in our SIM. That's something that I wasn't expecting. Maybe it's a property of the parameters that are used during the reconstruction step, but it's quite interesting to see. But in all cases, we've still managed to extract the information that we wanted, and that's the location of the lithium within the actual cathode material. So this is all really promising. It's set us up and motivated us to then apply this in practice. It's very difficult to do in practice because these materials are so sensitive, even during preparation to air. You have to be really strict with how you treat them. And then to get them and actually image them without destroying them is very hard. But we're hoping that in the future we'll be able to do that. So in terms of conclusions, all the phase images were great. And something that was really good to see was that our phase images were a lot better than our annular bright field images. And that goes really well with what was found in the literature, where here we have on the right our phase images and then annular bright field images on the left. And we see that the phase is a lot more robust than the actual annular bright field images. But the key to all of this really is speed and to be able to do 4D STEM fast. As Nigel mentioned earlier, one of the problems with 4D STEM is actually the amount of data you have to carry with you. So for example, typically maybe 4 to 10 gigabytes upwards of data is required, when in reality, you probably only need about 30 megabytes of data to be able to recover all the information that you wanted, which for us at least is something that we're really interested in, because again, in processing and live processing of this data, you could imagine then, well, if I've got a much smaller data set, I can process it a lot faster and I can on the fly do my phase retrieval. And that's something that really is the key, and it's all about speed and low dose. So I'd just like to say thank you to all the co-authors, notably Laila Mehdi and Yanis Siachos for their insightful knowledge into these materials. I'd also like to thank Jacob Madsen for developing Abtem, which is the simulation code that I used. Thank you to Rudy for some of the funding to be here. And thank you again to the organisers. I've also got a QR code up there, which is the same link which Nigel had on his slide. If you want to try out our algorithm at any point, there's a free demo you can use, and also links to all of our LinkedIn profiles and stuff like that. So then you can keep up to date with anything that we're doing in electron microscopy. So thank you very much, and I'm happy to take any questions.
Thank you, Alex. Do we have any question? We have one online, so maybe we take first the one online.
Okay, so we have one question from Laurent Clark from the University of Luxembourg, if I'm not mistaken. No? What is this? Okay, whatever. So how do they scale between those in PA to electron per probe position?
Yeah, so essentially it's quite a straightforward calculation to determine how many electrons you have incident on a probe location based on the probe current. So in this case, we assume that the number of electrons which come through the probe then hit our detector. That's a fair assumption if you've got a thin sample. And then essentially you can determine based on the charge or the charge of the elementary charge, you can then determine how many electrons should hit your detector or should go through the sample. So really in this case, in terms of numbers, probably talking on the order of 10 to the 4 electrons per angstrom squared with these sorts of probe currents. So then when you start introducing subsampling into that, you're then dropping down by a factor of 10, and then maybe by a factor of 100 if you start taking other considerations into account. So our realistic dose is more like 10 to the 2, 10 to the 3 electrons per angstrom squared.
Okay, thank you for this answer. Just one small correction. She's from the University of York. I misread.
Yeah.
Thank you. Any other question?
Thank you. One of the, I guess, in ptychography, in order to solve the phase retrieval problems, there usually needs to be oversampling in some sense, right? And I guess it would go against the other end of subsampling, meaning you try to drop samples. How do you balance or plan to balance those two?
Yeah, so in the case of iterative algorithms, you need to oversample. You need what we call probe overlap to then be able to infer what the phase should be there. In this case, for the WDD method, each seabed is treated sort of independently from one another in that case. Now, we postulate that you could do this for iterative algorithms, because then by applying the in-painting, by sort of rotating that data set into real space out of the fraction space, then you should be able to in-paint and then still basically artificially make that overlap, if you know what I mean. So that as long as you can do the in-painting, you can get the overlap. That's something we have tried. We've tried that and it worked well. You are sort of limited in how low sampling you can go, but then there are other methods where you can actually reduce the amount of overlap down from typical numbers are 87%. We tested going down to about 9%. That's some of the work that Amir's been doing at Liverpool as well. So using a different method for that. So sort of approaching it from two sides, focus probe and then the defocus probe stuff. Yeah.
Thank you. Question?
The WDD basically is only defined up to a global scale, right? A global phase shift.
Yes.
So would that be a problem, like since you're trying to merge different ones of them?
It's not a problem that I've found yet, because as long as, so if I go back to this sort of this stack of images here, as long as the contrast is retained in each of these virtual images, and then each of the diffraction patterns, which is then in-painted when I rotate the data back, as long as that remains the same, then it's all basically down to retaining the contrast in these virtual images. So then any global phase shift is sort of arbitrary in that case.
Thank you. Any other question online? One question related, I mean, for the reconstruction here, it's, I mean, for the in-painting part, it's with dictionary learning.
Yeah.
And I was wondering, like, if that would make sense in this context where you have like, I mean, a kind of structure that is replicated many times on the image, to have like the variant of dictionary learning that is called convolutional dictionary learning, where you could impose, I mean, this strong constraint of, I don't know if something you have tested or.
Yeah, so I think what sort of alluding to there is the fact that each of these dictionaries will probably be very similar for each of these layers. So you could, in effect, train one dictionary, or say, update this dictionary through some number of the actual virtual images. And then after that, you wouldn't have to keep updating. You could change the actual learning rates of the process. That could, again, potentially improve the actual in-painting result. This is the only way we've tested so far that is just this independent sort of dictionary learning process for each of the virtual images.
Thank you. Any other question? Okay, so thank you again, Alex, for this presentation.